change a little bit now from the type of loading we've done so far. Well, we've done two types of loading. Axial loading, where the forces are in the direction of the greatest dimension of the piece. So something like that. We also have looked at torsion, which is the of course some kind of twisting load on the piece, as we might see in drive shafts and the like. Now we're going to add to it actually the main type of loading that we saw in statics, which is the loading that causes bending, which is for most of what we'll do, at least certainly in this early part, transverse loads, transverse to the across the axial length of it, across the greatest dimension. And that's, if you remember, an awful lot of what we did in statics, a whole bunch of those kind of things. Spent some time learning just how to find the reactions. What we're going to review again then this morning is the shear and moment diagrams we get from that, because what's going to be a big concern to us now is how these beams respond to this kind of loading. It's not any great shakes to know that these are going to bend something like that, but any place you've got a curve in the beam like that, that's internal moment, and we need to look at that. We need to see, can the material withstand those kind of loads? There's also, of course, shear across here, as well as the internal moments. And then a little bit later, more near the end of the term, we'll actually look at what is the displacement of the beam at any one place. It's actual deformation, just like we've done with the other two loadings. We looked at the loading first, made sure the material could withstand the loading, and then actually looked at the deformation. And if you remember, for both of these, and it'll work again for this, it allows us to determine the reactions of statically indeterminate type beams. If you remember, our simplest type of beam support was a support of some kind like that, such that it was pinned at one end, but we had that little roller at the other end. Because if we had actually pinned it at both ends, which is pretty much what any of us would have done if we were actually building something. If you're going to put up roof joists in a garage, you're going to nail them down at both ends. You're not going to nail it down at one end and then put some kind of roller at the other end. Nobody builds a garage that way. But this type of support is statically indeterminate, meaning with our equations from statics, which was nothing more than the sum of the forces and the sum of the moments, with those three equations, we could not solve for the reactions. If you remember, pinned type supports, and this isn't loaded yet, but if it was, we know what to do with it. The pin type supports supply a reaction in both of our ordinal directions, and that gives us 4 unknowns, and we only had 3 equations. So it's going to be this actual deformation that will allow us to find a 4th equation, where we're going to actually come up with ways using the deflection of the beam as a way to solve the statically indeterminate problems like we have there. Other ones we looked at, we had we were certainly able to solve the reactions for that kind of beam when loaded. However, if it was that kind of support, then that we couldn't solve. But now we're going to be able to, as we add in the actual deformation of the pieces. Just like we did with axial loading and torsional loading. So let's do a couple problems. We'll spend today just reviewing our ability to put all this together in terms of a shear moment diagram. Well, one of the things we're looking for the most is not necessarily the internal shear in the moment at any one place, but where it's a maximum, because we could certainly come up with the ability to design beams that can withstand the maximum moment, the maximum shear at a certain place. Maybe we don't need quite so much beam somewhere else. And that would allow us to save some on some of these beam designs that we're going to be working on now. A little bit of a reminder, what we're going to be doing, of course, is graphing the internal loads, the internal shear and moment. And if you remember, as we did that, we had a convention for what's positive and what's negative as we look at these. Any shear that's down on the right side and up on the left, and by that I mean as we expose the internal structure of the beam with our imaginary cuts through the beam. Of course, these beams are imaginary anyway, but we imagine a cut through those to expose those loads. And then any moment that is in that direction on the two either ends. These are what we arbitrarily call as positive values. Anytime we have actual shear and moment in that direction on either end of those exposed cuts, we'll arbitrarily call those positive. What we're most concerned with is where the maximums are. But as you'll see with when we really get to the design of these beams, the direction is going to be important too, because not all our beams are going to be symmetric in all directions. For example, if we're looking at a simple cross beam like this with some internal moment, we're going to find it's quite different which direction the bending moment occurs, whether it's positive or negative, for a T-beam like that. That's the cross-section of the beam itself. Everybody's pretty familiar with I-beams, and of course just regular beams, but we're going to look at lots of the possibilities. We're not going to look at all the possibilities, but we're going to take into account all of the generalities that we can as we start to design these beams. So in a few weeks, actually probably just right after break, if I remember, right after break, we're going to be looking at what the cross sections are and what those mean, and why I-beams and H-beams and box beams and other kinds of cross-sectional shapes are so useful and important to us. So let's do a problem just for review, just like we would have done in statics a couple weeks ago, just before Christmas break. We were doing stuff like this. So someplace here we'll put a pin. Now remember, all that does is keep the beam from either going up and down or left and right, but it doesn't keep it from turning. That's a simple pin support. And then we'll put a roller support right at that end. And then the loading that we'll put with this is 20 kilonewton load there, and then not quite in between, a little bit to one side between the two supports, 40 kilonewton load there. And the distances between each of these spots, .5 meters there, and these are, of course, in all of these are in meters. 3 meters there and 2 meters there, so not quite to scale, they're pretty close. And all of these in meters. All right, so there's our general setup. Just for help, we'll label the main spots, the places where something changes in the loading. Either a support comes into the problem, or some kind of extra load is added, or some major part of the load has changed. So if you remember, what we typically did was start from one end, measured X from there, so that we'll be able to get the shear and the moment, the internal shear and moments, as functions of X, and then we'll be able to graph that with these. And I thought about it since we last did it a little bit, and I came up with a way that might help to make sure that we get the signs right on these as we go to graph these. One thing that can work is once you put in the unknown internal loads that we've exposed with our imaginary cut, sketch them in as always in the positive direction. Then just simply solve for them and graph the values that you get straight away from that. For example, it becomes a simple matter of summing the forces in the x direction. They're both in the same direction as drawn, so we'd say 20 kilonewtons plus V equals 0. Then when we solve for V, it's got a negative sign on it, which is useful because that's the number we have to graph. Again, my recommendation is that you draw these above and below each other as we go through these, so that everything just makes sense. You can use certain places to double check. So we'll graph the shear as a function of X as we go. And we already know between A and B, we don't have to do anything else between A and B because none of the load changes in that region. But from A to B, we know that the shear is minus 20. And since we put in our drawing the positive direction, whatever value comes out, that's exactly the value that we need to graph. So the minus is already on there. We don't have to reinterpret anything. It's a little bit different than we did last fall. Last fall, I think we typically looked at a down load here that we knew the shear would be up. We drew it that way and then had to interpret it for the drawing. If we put it in positive, just sketch it in positive automatically every time, then solve for it, and now our sign is there and we don't have to do any interpretation. So that may be easier. Maybe you prefer not to do that. It's up to you. But that's what I'll try to do from here on out. And then when you take statics again in the fall, that's the way we'll do it. There. Oh, by the way, did you see the note I put on that Binghamton has some online courses for the summer, I believe? That may be of use to some of you. Statics is one of them, but I don't think, if I remember, any of you need that. However, there are some other courses that you might want to take online there, just to put a little bit more in the bank at state prices without having to pay have to move down there. Is anybody thinking of going to Binghamton? Anybody thinking of going to Clarkson, by the way? Thinking of it? We have several scholarships available. What I need from you is a paragraph of why you might deserve one. And I can help you put that together. That's also true for RPI coming up in just a couple weeks. So start thinking, if you want to go to either of those schools, about putting a paragraph together for us. So that we can, and they're substantial scholarships. They're about $10,000 a year. All right, so again, then we sum the moments and know that they'll sum to 0. We have a clockwise moment between the V and the two V's, a distance x apart. We know that's in the negative direction. And then that's got to equal also a clockwise moment. Oh wait, and that's our positive direction for these. No, that's not going to work. These are in opposite directions. No, that's what I got. Yeah, these are in opposite directions. So, yeah, so I think we're okay. All right, so V we know to be minus 20. So when we put in the minus 20, we get 2 minuses. When we move it over to the other side, we get M equals minus 20x Newton meters. And then that's, if you remember, what we graph on the moment diagram. Sorry, kilonewtons, kilonewton meters. Starts at 0 because this is just a free end. A free end never has any moment in it internally. So starts at 0 and then goes down at a slope of negative 20 to a value of, when x is 2.5, 2.5 times 20 is 50. And so we get that kind of picture down to there. Helps to hatch it in a little bit, I think, just to illustrate what's negative, what's positive as we go through these. All right, we can continue on. Nothing again changed until B. Once we get from B to C, we do have a bit of a change, so we draw out to there. We've got that load there, 20 kilonewtons. We now have one of the supports at 2.5, one of the reactions. That's a reaction at B. Oh, we didn't do those, so we have to figure out what those are, but that's a fairly quick matter. I'll put them in for you. You can check them. B happens to be 46 kilonewtons. Remember, we get that just like we were doing the first month or two in statics. Do that on the whole beam. I was just so intent on getting to the internal loads, I wasn't paying attention. We had to come up with these external loads. And when we get to it, D is 14 kilonewtons. No, not 20, 46. All right, so we need to figure out what the internal loads are and draw them in as positive every time. Then when we solve for them, we'll get the direction, we'll get the number we have to plot straight away. So summing for the shear there, the internal shear, we've got 20 down, 46 up, and yeah, that was okay. And plus V. I'm not as used to doing it this way, so I got to double check. Yeah, so we get then, no, down, huh? We'll start with the V. We know that's positive. V, let's see, the 20's in the same direction, the 46 is in the opposite direction. That's all for kilonewtons. Let's see if that works out. Maybe it's better the way we did it before. Oh, what we did before is everything up equal and everything down. So that's what we got here then. So V equals then minus 46, but it goes over the plus 26 kilonewtons. Which, remember, is what we'd expect. We have a reaction of 46. We know there's going to be a jump of 46. That puts us at the plus 26. And then that goes all the way across to C because there's no change in the load there. So that jump from down here to up there is in the same direction as the reaction, and so it works out okay. All right, then we sum the moments. Remember X from the, where did I draw it? There we go. X as measured from the left side. So we know we've got 46 X kilonewton meters. That's the moment caused by the first one. If we're doing moments about that end A, then minus V X plus M equals 0, where M is that internal free moment there. Okay. Oh, sorry, this it's not 46x. It's 46, we know that distance, it's 2.5. We all need a review on this. There we go, fixed. If you remember, we've got lots of double checks that would catch all the little troubles here and there anyway, so then we get solving then for M. 46 times 2.5 is 115. and the V that we had in there is the 26. So yeah, so we're okay. 26x minus 115 kilonewton meters. So we have to graph that. It's got positive slope because this is 26x. The intercept is minus 115. Remember, that's where x equals 0. So that's somewhere back here. I don't know if that's that much useful to use. But what we can do is notice that this is just a simple pin support, which means there's no additional moment caused by the support. So our line starts from the point where it left off. We can then draw our line from there with the slope of 26 from there and over a distance of 3. Then we can find out how much that moves up. It goes up to about 28. So if that's 50. We know that if x equals 3 beyond point B, we're going to go up to a 28, so then we can draw that straight line there. And that will have our slope of 26 automatically. So again, what we're looking for is, for the most part, is where's the greatest shear, where's the greatest moment, and we'll be a little bit concerned later on, more concerned later on with just what the direction of those moments are, because that's going to tell us where the bending, what the bending direction is. And then the last piece, from C to D. Remember, we have to do this every time there's a change in the load in some way. So we have that there. We have B here, which is 46 kilonewtons up. We now have the 40 kilonewtons down at C, and now our cut is somewhere between C and D. Draw on the shear in the moment and just solve for them. All the down moments, V plus 20 plus 40 equal all the up moments, 46 kilonewtons. And so we solve for V there. Let's see, that's 60, goes over, becomes minus, what, minus 14? I think, yep. Which it should be, because we finish with a support of 14 over there. So now we can draw on the moment at, just using the value that came right from assuming in positive direction, gives us an automatic negative sign. And now we've got the shear diagram completed. And it agrees because we jump up 14 to the end, and there's no additional shear at the end. So we finish just as we should. That was pretty simple. Let me just erase that and do the moment. So we've got a positive 46 times 2.5, which we know to be the 115. And the the opposite direction is 40 times 2.5 plus 3, 5.5. All of these are kilonewton meters. And then also in that negative direction, V times X.
Why is it 46 more positive? Why isn't it the other way around?
Just
Oh, I got it. Never mind. I wasn't paying attention.
and then plus M.
Matching the other one, I see.
Yeah. And so all those numbers come out to be, I think if we put them all together, let's see, the V is minus 14. So when we solve for it all, I believe we get minus 14x plus 105 kilonewton meters. Minus slope makes sense because we know we have to come to this roller support end, which will have no internal moment left in the beam. So we know we have to finish at 0. So the minus slope makes sense. And if we put the values in, we know that we don't start, or we start exactly where we left off at the moment. And then we're able to finish our moment diagram. Remember, the slope is V at any spot in the same place. So it's 26 there, minus 14. So the slope of the moment diagram is the same as the shear. Remember too that the area of the shear diagram between any two spots is the change in the moment in those two spots. So all of these things should check. Even if you do get a minus sign wrong somewhere, you should be able to catch it with these checks that we can do. And so let's even use that to our advantage and do another one. So, cantilever beam, which means it's embedded in the wall. So, to midpoint, there's a uniform load distribution. Remember, that's in units of pounds per linear distance of the beam itself. So 3 kips per foot there, out to a distance of 8 feet. And then just to be nasty, we've got an extra structure in here upon which there's a load. Put it up kind of high because I want to get the drawings in below it. 10 kips. And the distances are, this is 3 feet. This is 2 feet. feet left over to the wall. All right. So first thing we can do is figure out what the reactions are. How much room am I gonna want? So there's that load. What can we do with the load caused by this little bit of superstructure there? Remember what we can do with that? Because of this moment arm here, that superstructure is going to cause some bending, some moment to be applied around that point. So we'll replace it with that, an applied moment of 10 kips times 2 feet, 20 kip feet. But that 10 kips down is also pushing on that point, so we need to add in that effect. So we can replace the superstructure there with that 10 kip load with a moment and a just a straight load of its own. And then also need to figure out what kind of support reaction is there. Label that in A, B, C, and D. So that's the load D. But it also affords some moment to it as well. And we can figure out what all of those are. Remember, replace this distributed load with an equivalent point load at its excuse me, at its geometric center. It's a centroid of area. Remember, the magnitude of this is the area under the load curve, so it's 3 kips per foot times 8 feet. So that's an equivalent of 24 kips. That's only for the purposes of finding the reaction. Once you do that, solve for the reactions, you should get that this is 318 kip feet in that direction, and the reaction in D is 34 kips. All right, you can double check those. And then we can draw our shear moment diagrams. And we can speed it up a little bit if we remember some of our graphical relations between these. I happen to know offhand that we only have negative shear on this one, so I'll I can go ahead and draw the axes like that. Just to make it a little bit easier for us. What's the shear at this end A? Chalk dust getting you?
0.
Yeah, it's a free end. There's no load until we actually get into the beam some distance. So we do know we start at 0. Then do you remember what the shear is in relation to the distributed load? Do you remember what that deal is? The relationship between the distributed load, which we call W, as a function of X. Remember what the relationship is between W and V. The opposite of the shear load is the slope of the shear diagram. So that's considered a positive load because that's the typical way loads are. So we have a negative slope of 3 kips per foot. And that would go for 8 feet, so it would take us down to about 24. Which, so I can leave enough room. Is something like that. And we can do that remembering this relationship between the shear and the distributed load without having to actually make the internal, the imaginary cuts and figuring out the internal loads there. Also turns out, I know ahead of time, that all of the moment is negative, so I'll draw it like that. Save us a little bit of trouble. Kip feet. You know the moment at A, since that's a free end, is also 0. What's the relationship between the shear and the moment diagram? Well, it's the same thing we've got here. We know that the slope of the moment diagram is the shear. And we have a increasingly negative shear, so we have an increasingly negative slope on the moment, which is a parabola concave downwards. Just where it goes to is a little bit difficult to figure out unless we remember the opposite of this is that the change in moment between any 2 spots is the area under the shear curve between those same 2 spots. So the area under the shear curve will tell us where the last point is, and then we can sketch in a parabola once we have that. 1/2 the base, which is 4 times 24. What's 4 times? Is that 96? So we know we go down to a minus 96. Let me leave myself enough room. We're going to have to go a little bit deeper later. And then we can draw in the parabola like that easily once we have those 2 points. We know it's at 0. We know the slope is at 0 as it comes in because the slope goes down to 0 as a V goes down to 0 coming into that end. All right. see, there's no change in the load, so there's no change in the shear. And there's nothing more we need to do. We know it's going to do just that. We know that the moment now has a slope of minus 24 from there on, and the slope is continuous, so it actually, we continue the line straight where the slope left off. I think we're going to, as often happens, we're going to have to redo this drawing, just because we're kind of running out of space here at the bottom of the board. We know it ends at whatever this area is right there, which is 24 times 3, which is, what, 72, I think. So it's an additional 72 beyond the 96. Which is, yeah, 168, I think it is. And that, yeah, that agrees. So we're down here to a 168 minus 168. So that's our change in slope, change in moment from the point where we just left off to the point where we're now finishing, because that was the area of the shear curve right there above it. And we can continue. Now we know that we have a 10 kip load down, so we just simply draw that on the shear curve. Takes us down to about a minus 34. And we know there's nothing left over till we hit the wall, where we come up 34 to the wall and finish the problem. And so everything matches. Now in the moment diagram, right at this spot, we have an applied moment of 20 kip feet. So that's going to cause us to jump up by 20. That takes us to 148, right about there. Yep, we're going to run out of space. So I just have to make my curve a little less deep. So that was minus 96. This is minus 168. We jump up by 20. So that's a point moment applied to the beam and the response of the moment curve to that. Then we know it continues from there on with a slope of minus 34. So it's going to be negative in some measure, and we can figure out just how much by calculating that area. Minus 34 times 5 is 170. So we go down a further 170 from where we are there, and we're at minus 148. So 170 plus 48 is 318, and that's where we expect to finish because we have this applied load, applied moment due to this reaction support there. So it takes it down to a minus 318, which is just what we'd expect to get back up to the end of the beam. And that slope is minus 34. And we've got the shear moment diagram. And as happens, sometimes you need to resketch them a little bit. Okay, so remember those relationships. Didn't happen to use it, but it can be very useful. That it's also true that the change in the shear is going to be equal to the opposite of the area under the load curve. So we have those four relationships, plus any of the point values that we happen to understand, especially at the free ends or at the reactions. Combine all that with the known jumps because of either applied loads, moments, whichever might work, and we can complete these. What's going to be of concern to us for the most part in a bit is what are the maximum values on any of these, because that's where the beam's most likely to fail. And we're going to start designing the beams now to prevent failure. By designing the beams, I mean we're going to pick the size and shape of the cross sections of the beam. It's the cross section of the beam that's going to be able to resist, well, and the material, of course, resist these maximum shears and maximum moments. All right, so one for you to do. Again, a cantilever beam, and it's split into thirds. With a 19 kip load, sorry, not kips, kilonewtons. Three meters there, and again at 3 meters, we then have a uniform distribution of the load. So beam split into thirds like that, and the last, oh sorry, not 3, 2. Not that it really matters, we're making it up anyway, but at least it'll agree with my numbers. And a uniform distributed load, 3 kilonewtons per meter. All right, so you come up with the shear moment diagram. That's it. Don't worry, if you do well with that, I have another. All right, so you come up with the shear moment diagrams. Go with that. I'll help you a little bit, just let you know where the axes are. Sometimes we need a lot of negative axis, sometimes a lot of positive, some fairly even. These ones are fairly even. A little more negative than positive needed. don't forget, first you need to find the reactions. And since it's a cantilever, there's both a moment and a shear applied there. Just to help you out, that's the direction of the moment on that one. Which is a little different because that 19 kilonewton load is up. So it actually makes the moment in that direction supplied by the wall. So use any of the graphical methods, use any point values that you happen to know just by observing the beam, and if ever need be, you can always make the internal cuts and figure it out like we originally did before we established those graphical methods. Whatever combination of all of these things, all of the hints that are there for the values, you can make use of as you wish. Chris? So, whatever you can come up with. You can look at the beam and usually get at least a few of the points. Might not know what the line does in between, but you can place a few of the points, usually at the ends. In fact, the moment curve, the value of the moment curve actually tells us how the beam is going to deflect, how it curves because of the loads. Of course, the solutions are online, so you can check any. So you got to figure out the reactions. Shear is usually pretty easy to come up with. Moment tends to be a little more subtle, but if you just make all the checks and balances we have with all these different clues that are here, you can usually put it together in pretty good stead. Something conflicting? You have that posture. Now, be careful. A lot of you are missing something. Remember, we can replace this with an equivalent point load of 6 kilonewtons. But that's only for the purposes of finding the reactions. Once you've found the reactions, you're done with that. You're done with that equivalent point load there. So we have 6 kilonewtons down. 19 kilonewtons up, so A is actually in the wrong direction there. You're going to get an A of minus 13. So that's your starting point to give you enough room. That's actually the biggest value we're going to get. Because of that upward 19 kilonewton load, the wall is actually holding that end down, not holding it up, which is usually what we see for a cantilever support at the wall. Then you know there's no more load on the beam between A and B, so it just goes straight over. That help? Travis, that helped a little bit? Shear diagram is usually a lot easier because the jumps in the shear diagram go in the directions of the point loads, which helps a lot. Yeah, so most of you are getting that it jumps up 19 to a plus 6. And then nothing happens in between. Shear, we're not so much concerned about the direction of the shear when we start designing the cross sections and the materials and the like. We're concerned with the direction of the moment, so as we'll see. All right, now we know that the slope of the shear diagram is minus the moment, and we get to a free end. So we know we finish at 0. So it's a straight line coming in. For the moment diagram, it helps a lot, I think, to remember that relation, that the change in the moment for any section is the area under the shear curve between those same 2 points. So I think that can help a lot. We don't start with 0 moment, because we have the cantilever support there. We do finish with 0 moment because it's a free end. But a cantilever support will supply internal moment. What that means is right at that point the beam is already going to be curved some. The final shape of the beam will be horizontal. The slope will be 0 there, but it'll immediately start curving. And because of this unfamiliar 19 kilonewton load up, it actually curves up there, as we'll see in a little bit when we stackers. Actually, look at the deflection. Got it, Chris? You think? You're covering it. Let me see it. No applied moments, so there's no jumps in the moment curve anywhere. There's breaks in the slope, discontinuities in the slope, but not any discontinuities in the curve, the line itself. There's no applied moments. What do you have for the moment supplied by the wall, the reaction supplied by the wall? You're going to need that. That's going to give us the starting point on the moment diagram. It's not zero there because of the cantilever support immediately puts a moment in the beam. And you can figure it out by summing the moments about A and using the equivalent point load of the distributed load. Be careful, don't forget that's not actually there. Because of this right here, in our relation. That, a distributed load down is considered a positive load. So we put a negative on it, and then the slopes match. That's the only one of those relationships that has a negative sign in it. Well, I guess it's equivalent one of delta V does. And that would all match with our convention of positive directions. Going to need that moment at the wall. That's in the proper direction. Do you have the magnitude of it? Of MA? I drew it in the right direction for you. I didn't happen to with the A itself, but I did with the MA for you. So if we draw that in, with MA in the proper direction, nobody's yet given me the magnitude. We have A is actually in that direction. Without that wall, that end of the beam would go up. And then if A is down, we know we want shear going up, so that's why it's negative there. That's our negative direction. But the moment must also be in that direction. And so when X is 0, we're right at the starting point. There's no moment due to the shear. We know that we start at MA and it must be in the positive direction. Does anybody have the magnitude for this? 9.7. 9.7? Not quite what I got. 8 is what I have. And that's in that proper direction. So, what units per kilometer meters. So we actually start at 8. No, this upward 19 kilonewton load actually makes these reactions on this cantilever opposite than what you'd normally be used to. We're normally used to everything on the beam pulling it down, but that actually gives it a net effect of going up. That's what you, it's wrong, but it gets extra credit for creativity. It's an awesome try. So if you know it starts at +8, you know what it does from there. Goes down from there, straight line because of the constant negative shear. And we'll finish at a distance delta M below 8. Which is what? 13 times 2, 26. So it finishes at -18, is that right?
Yeah.
So that's +8, so how about 2.5 times that? We know that it's a straight line down to there to -18. Because that's what the delta M was. You don't have to actually figure out the slope. You don't actually have to graph the line. You know it's going to do that. No. Look at the shear diagram. It's positive. So shear diagram then turns positive and constant. So we have a positive and constant slope. And we can figure out the delta M for that space. That's just a 12, so it goes up to, what, a -6? Which would put it right about there, I think. At -6. Yep. So we have those two slopes, -13 and +6. And you finish at a -6 there. Then it should be easy to finish. Yeah. You're going to stay with that one, Chris. I may have to put that up on the projector to share with the class a rather unique answer. Phil, don't you wish you'd come up with that answer rather than whatever you have?
That's not how it takes.
Pretty awesome. So we didn't have to actually do any imaginary cuts, didn't have to break any of them in there. And then, yeah, you know how it finishes. Yeah. Slope is continuous. There's no break in the slope here, no break in the the curve itself. There's no applied load. And we know we finish at a 0. So continue the slope, but then start curving it in and bring it in then to the final little bit. You can bring it into 0 and you've got the whole curve. And all of the stuff agrees there. The area of that should be -6, and indeed it is, or +6, because that's the change in M that we see there. All the slopes agree. Shear goes to 0, so the slope of the moment curve goes to 0. And we're done. All right, any questions on those? Friday, we'll start talking about what all this has to do with how we actually shape the beam, decide on the beam cross-section itself. For the most part, shear just needs enough area and needs an appropriate resistance to shear, but the moment's going to take a little bit more of our, a little bit more work, and we'll bring in a lot more of the tools that we developed in statics last fall for doing some of these things. All right, any wrap-up questions? Phil, you okay? Chris, did that make sense now? Even though yours is a lot better answer.
I think it's spot on.
Yeah. Don't you wish you'd come up with that answer? That's that's great fun. I think that's the first time I've ever driven to you that kind of frustration, Chris. I'm very proud of myself. I may have to put that on my resume, teaching qualifications. All right, that's a wrap.